Hello. I'll be talking about a few concepts that I call kick-off concepts in this lecture, and particularly I'll be talking about the categories of learning. How do we classify the types of learning problems? And then I'll walk you through a few other concepts um, related to the representation. How do we represent real world problem to deal with it with machine learning algorithms, or to learn from it, let's say. A few conventions that will be hopefully helpful for us going forward. And then I'll be introducing some aspects and fundamentals of evaluation. How do we evaluate actually our learned algorithms? Now, there are different ways or criteria according to which we can classify, and I need to be careful actually with the word classify. Let's say to identify the type of machine learning algorithm. I'd rather say the learning problem, and so there are different criteria to classify the learning, or distinguish between the different learning problems. And even though that there is no really theoretical component to this, but this is a simplistic, let's say, way of looking at the large spectrum of algorithms and learning problems, and the few learning problems that we usually deal with. And so the first of this set of criteria is human supervision, or whether there is an intervention from the human into the learning process, and I'll define it shortly after this slide. The type of output, whether that output will be, let's say, an orange as per the example of last week, or another type of fruit or object. So you can think of a binary classification: yes, no, pass, not. Or it could be, for instance, a numeric outcome. A numeric outcome would what would be the temperature for tomorrow. That is not binary. It could be binary if you'd look at the problem as the required output is one that relates to whether it will rain or not. But if you are concerned about, say, what the temperature of tomorrow would be, then you'd be concerned or looking after a model that learns and predicts as a result a numeric output which is mostly continuous within a certain interval or valid interval. And then, but also you can have types of output which are sort of a probability distribution. And so you'd say, well, the output is not an apple and it's not an orange. It's, say, 63% of the time it would be an apple, and the rest, which would be 37, for instance, percent, would be an unidentified object, or say a banana. And then the learning frequency, whether actually the learning process or the algorithm is more than the algorithm, the learning problem is one where it needs, or the output relies on continuous learning process rather than one time learned model. And so if you'd want to think of a learning frequency type of problem, say, probably I'll give an example more thoroughly later on, but think of the GPS of estimated arrival time. If you are driving, or say cycling, or even walking, but probably the driving gives us a better tangible example. So the data which are fed into the algorithm is data of passengers, or people who are on the road in their cars, trying, say, to go. If we are going to, say, Gatwick Airport from Bristol, you'd be thinking, okay, in 2 hours 40 minutes you are estimated to be there by, say, the North Gate. And whilst you are hitting the road, of course, there are parameters that, or input that comes from you, which is your speed, but also that of others who are using the same application and feeding the information to the app of, say, Google or Apple. And then imagine if there is, say, a passenger who was supposedly going an hour before you, and the duration was calculated to be 2 hours and 30 minutes, and it took him or her 4 hours. And then, even though there are no cameras or whatever, there would be an expectation or like a factorization, or sorry, factoring in other potential, let's say, events that had happened, other likes of, say, congestion, or say an accident, and so on and so forth. Now, obviously, there is also the idea of pattern detection throughout the day. Is what hours are more busy, and as a result, it takes longer to get to the destination, and so on and so forth. That you could think of as an instant learning process. You can learn actually throughout the years, or the days of the year, and the week. The average length or duration of the journey, if you take it midday, or on a weekend, on a Sunday. However, that during the trip itself, you'd see that those algorithms are learning on the go and being fed with information. Now, prediction mechanism is essentially whether you are creating a model, and usually we call it parametric models, i.e., you basically say, if I have a Cartesian plane, a two-dimensional plane, let's say, and I have dots and stars, and I can come up with a curve between both of them, both clusters or both objects, that line becomes a model. And you actually thereafter, in order to do predictions, you can discard those that were plotted on the plane and say, well, this, what comes on the right side of this curve is stars, what comes at the left side of this plane is dots or circles. Now, in other instances or types of learning problems, you actually don't come up. Now, these models, by the way, are generalizations. So they are based on assumptions, and some mathematical assumptions, and some intuition as well, in order to come up with this model that generalizes. And you'd say, okay, well, I can deploy it now, and I can use it to predict whether it's a benign, say, cancer or malignant cancer, in this, if you are having a binary classification problem. Whereas in some other instances, you actually don't generalize. You don't come up with a general model to describe the function that distinguishes between the two types of potential observations. But you use the data itself, and many of the, say, density estimation kind of methods relate to this type of problem. And so you would think of a student coming late to the classroom, and you'd say, okay, well, what type or what program is he or she enrolled in, whether it's an MSc Data Science or MSc FinTech or MSc IT or a PhD student. And this can take us very long to talk about, but essentially, a characteristic of the natural phenomena is that we tend to cluster based on similarity metrics. So people who are similar to one another tend to cluster. I mean, if you think of recommender system problems and applications, they actually are delivering recommendations on the basis of clustering us into different groups, behavioral groups, or taste groups in terms of cinema, for instance, or music, or reading. And so an instance-based rather than a model-based in the prediction mechanism is one where this student happened to sit next to a fintech student. And so you'd say it's most likely that this student is a fintech because he or she sat next to a fintech student. Whether that is right or wrong, you can validate and see on the given data set that you're provided. But for the most part, usually many problems can be solved or can be learned through density estimation algorithms. Now, I think I've talked about most of them very arguably thoroughly, but just to make sure that we are talking with the definitions, even though simplified and high level. But here you go. I mean, the human supervision or intervention, whether or not they are, or I mean, the models or the algorithms are trained with a human supervision or intervention. So supervised, as I mentioned last week, the ground truth is provided with the samples or the observations. So you have a bunch of objects, including fruit, but also you have recorded next to each fruit the name of that or the type of that fruit. And then the question becomes how to learn the features of these objects and relate them, map them to the name which is provided. And so in the future, you'd want a model whereby I give you the texture, the size, the color, the taste of the fruit, and you'd want to predict what fruit that is, whether it's a banana or an apple or an orange, okay? But then the idea that the data itself, the labels, we call them labels or ground truth or annotations, are provided with the samples themselves, on which we train usually the models. Now the unsupervised is completely the opposite. You have the observations, but you don't have actually labels. And I related this to clustering a certain star in galaxy A or galaxy B. Obviously, the galaxy A and galaxy B do not really exist as such. We call them A and B. And so what ends up happening is that you basically, or for instance, an alien comes in and lands on planet Earth, and they are asked actually to classify the objects on Earth planet. And they don't know that we are humans and animals or objects and tables and cars and airplanes. What they end up doing is that clustering the planes together because they share certain attributes, or there is a more internal similarity between such objects compared to intrasimilarity between a plane and a human being. Okay, so that is unsupervised. Now, you don't have a ground truth, you just look at certain similarity metrics whereby you end up identifying clusters or classes of samples or observations that can be put together. Now, semi is a combination of both. You have actually a sample of the data, say a bunch or a basket of fruit. Some of them are named, say, almond and banana, and the orange, one orange happens to be unknown, the one word which is written on it, or simply it's not provided with the name. And then you have the reinforcement, and I explained it. Now, reinforcement learning, explained it last week with the example of walking in the room or the smart vehicles. And these essentially, you don't have a ground truth. It's like an agent running in a dynamic environment, and this agent is going to learn through its interaction by means of rewards and deduction of rewards, or punishment, if you will. And obviously, reinforcement learning basically is not essentially a machine learning. I mean, even though there are applications, but the typical applications of machine learning does not involve reinforcement learning. I can debate on this very far, I'd say, but I think it's out of scope here. But if you are interested in applications of or theory of reinforcement learning, maybe we can talk marginally about this or individually about this. Cool. Now, the types of output, I refer to the binary, whether it's an orange or not orange, and that is called classification, especially when it relates to, or it's related to supervised learning type of problem. So you can actually take that supervised with the classification. It's essentially like that, the same type of problem. We just use different criteria to classify them. But anyway, so that is a classification, whether you are a fintech student or MSc data science student. And here I'm looking at your attributes. So your age, your say gender, where you come from, your background, what modules you chose, and then I'm asked to predict whether you are MSc data science or MSc fintech. Now, the other one is the regression, where I mentioned also the idea of that, or the purpose of the learned model is to predict a numeric value, a continuous value within a certain interval, as I mentioned earlier. And so the temperature of tomorrow is going to be predicted, say, with autoregressive models or moving average models, or now you have, for instance, recurrent neural networks or the simple linear regression model. So all those models basically give you an estimate, a numeric estimate of a variable that corresponds to a future time instant. And the clustering and the regression, by the way, is also a type of a supervised learning for the most part. Well, actually, not for the most part, it is a type of a supervised learning, except that the output is not a binary or a discrete output. It is nonetheless a continuous numeric value or real value. And then the third would be clustering, and the clustering corresponds basically to the unsupervised, and so it's like classification with the absence of ground truth. So again, the clustering is classifying us, the objects on planet Earth, by an alien into different types of clusters. So this cluster are where me and you and the dog and the chicken are put together because we are, let's say, animals to the alien, and the airplanes and the cars and the bicycles are machinery, for instance, or moving instruments, let's say, and so on and so forth. Now the density estimation, and I'll give you another example about density estimation later on, but because we are talking about another algorithm which is about this density estimation. Density estimation is again derived from the idea of natural phenomena tend to have a special pattern in clustering, and so general functions, for instance, can be explained by density function. So how to put it differently? You'd say if you look at the distribution of people where we live, say, next to businesses and public sector job providers, and occasionally we live next to water. Not occasionally, many occasions we live next to water and natural resources, and it depends. I mean, if you look at how people evolved actually living throughout the history, look at modern cities and old cities, for instance, depending on such and such requirements, people tend to choose different types of or locations. Now, if you'd want actually to think of, if you drop somebody from the space on the planet and this body will end up landing on some place, what is the probability that he or she will land on the, say, Indian Ocean? Obviously, if your reference here or your metric to calculate this probability is related to the space, I mean, then it is more likely that they will land on. But if it's related to actually your type of problem, which is where people live, basically the distribution of the humans, you will find that it matters actually how many people live in, say, London, in order for the probability of this individual to be someone who comes from London or will end up living in London. Okay, and now many natural phenomena, if you come up with a probability density function or a density estimation, you actually can relate unseen observations or observations of interest, say, probing tests or questions, and you can relate them, put them into this mesh of distribution. Okay, you'd say, well, it is more likely that they belong here rather than there, or more likely there rather than here. Now, dimensionality reduction is another type of output, and if you think about it, it's a problem which is reduced in dimension. So most of the time we say that the signal, when these are words that probably are new to many of you. There's a concept in machine learning, and actually it comes from signal processing, which is called signal to noise ratio, and that usually has to do with things like, the voice and the amplitude of voices, and if you heard of Fourier transform or wavelet transform, whereby you find actually that certain certain information is delivered within certain frequencies. Okay, maybe I'm talking really big stuff here and unnecessary, but the idea is that all signals is surrounded or usually delivered in nature with noise. And this noise usually does not really relate to what we want to predict or learn. So take this example. I use 10, 20 words to send a message, and this message can be summarized with 3 or 4 words. Now, what are the rest of the words that I use, the 17 words? They are essentially noise. I probably would want to convince you to go to party with me tomorrow in Bristol, and I'd be telling you how nice it is in Bristol overnight, how many, I'd be talking about your needs, the fun, about going with me. And essentially, the message is, go with me tomorrow to party in Bristol. And these are 5 words. Now, why it matters, actually, the dimensionality reduction. Actually, the more you reduce or you embed the information into a lower dimensional space, the easier it is for the learning algorithms to learn the real signal. And of course, the more effective it is. But I'll focus on the easier it is, or the to learn, because the models usually there are mathematical reasons. For instance, many of the models, say, of classification are geometric models, so they work in the the space, geometric space, and the more dimensions you have, the harder it becomes actually to classify or to find actually significance of the distance between samples. So that is on the one hand. I'll explain this really very thoroughly when we come to types of dimensionality problems. And the other reason is that it basically is easier for the algorithm to, and more effective, I mentioned, to learn from summarized, like condensed signal that has got the information, and you don't really confuse the algorithm with information that is not needed. Now, if you want to relate to another type of example, you can talk about, say, a records or table, allow me to call it table, of employees and their gender, their name, their whatever, and their salary. And so their name, for instance, or their origin, or their gender, well, there is a salary gap, but say their name. Even though you can go in anthropology to talk about lots of, does the name relate to the salary? But essentially, you would think in a utopian world that the name or the gender or the whatever has nothing to do with the expected salary or pay of somebody. It should be other attributes, the qualification, the years of experience, for instance, the place of, the location of job where they are working, and so on and so forth. And yet, when you are provided the information, you are provided information even of their ID, their nationality, their name and middle name. All this can be actually dismissed. Now, this is really a simple example of dimensionality reduction. We will talk thoroughly when we come to it. But I hope you understand now some examples or the motives of why dimensionality reduction matters. I just forgot to mention that dimensionality reduction per se is an output for model, which usually is used to learn further tasks in machine learning. So basically, the output of dimensionality reduction algorithms are used to do some classification or clustering. Okay. Now, the batch or online, and that is the learning frequency. I mentioned now on the left side of the panel, you'll see the batch, which is essentially so a one-time learning. And so let's say I have 10,000 objects, and I learned to classify the orange from the banana, and then I discard all the objects that I have, and I say this is the model, and I will use it for the rest of my life. Now, on the right side of the panel, you see what I mentioned about the GPS. You launch you learn actually the classes from the actual data, but when you run also you can use new data, and which is the people on the road if you relate it to the GPS example. Now, the types of the prediction mechanism, there are two types usually, or generally, there are two types of or two mechanisms to learning the problems that we tend to learn. One type is called instance-based learning, and the other is model-based. Now, as simple as it looks here, for the on the left side of the panel, you see an instance-based kind of problem or learning mechanism or prediction mechanism here. Learning or prediction is the same. I'm referring to the same thing. So that essentially the X or the cross here is the student who came late. And this is the distribution. Those triangles and boxes, let's say, squares, are the students' distribution in the classroom of machine learning. Okay? And so if you look at the feature 1 and feature 2 will be their location on the horizontal and the vertical axis. So, for instance, as you guys aligned, this student will be the bottom, the profound, the deep end of the room on the, to me at least, on the right side, okay? On the panel, it's on the left side. And this would be sat next to him or her. And this would be on the right or the other corner of the deep end of the classroom. Okay, well, this is a distribution of how the students are. And let's assume that the squares are the data science students and the triangles are the fintech students. A new student comes in late and sits here. And the question is, what is the program of this particular student? And you'd say, well, it is likely that he or she is a fintech student. Why? Because he's closest to 3 students. 2 of them happen to be fintech, 1 of them is data science. Now, I cannot really suggest or claim that this is right or wrong, but if it happens that for many, many times when a student comes or an observation comes and happens and you check, validate afterwards, oh, so are you really a fintech student? Yes. Oh, good. So you do it, and it happens to hold, and you say, well, this is essentially this is a k-nearest neighbor algorithm. This is an algorithm that we will learn in week 4. There are more to it, but simply this is the spirit of it. Now, why is this called a density estimation? As I mentioned earlier, well, essentially, the k refers in the k-nearest neighbor to the number of neighbors you would need to consider in order to decide the label or the class of the new observation as the new instance here, the cross. And so if the k is 3, I will consider the 3 neighbors as the 2 green triangles and 1 yellowish box. But if it's K4, I will take the 4 closest to this one. And now, actually, if you have more observation in one corner, they usually will have the majority of neighbors, and therefore they will dictate the label of the newcomer. But that is business for other day. Anyway, the idea here is that you don't really create any general assumption about to predict. You actually relate to the actual distribution of the samples that you have, and you decide for the prediction on the basis of the similarity or the distance between one object or one sample with regards to the samples which are located on the distribution. Now, you don't create a model, you actually just use the local distribution of the samples that you have. Now, on the other side, on the right side of the panel, you will see that I have a curve here. And this curve essentially is defined by parameters that I will tell you later on how they are or what they are. So actually, this line is what I call a model. And so once I create this line and I validate that this actually can separate both classes from one another, I actually can say, well, this model is something that I learned from the actual distribution of data. Now, I don't need the data in order to make predictions. I actually only need this model. Okay, so these are the 2 types of learning mechanisms. Okay, main concepts, and I will take a break. Now, let's take it step by step and go and see how we represent problems and how we build models. And again, this is really a very simplified step by step. We will be doing this tangibly as we go. So the question here is, or the test for us today is, or the challenge, is to build a model that classifies oranges from other objects. So you'd want to think of these other objects as you see on the right side of the panel that I have. Say this is a sample of the objects that I have, and some of them happen to be oranges. And so to refer to the conventions, we have a training set. What we have the data or the samples, these observations. Obviously, you now look at me and would say, well, how can I classify an orange? I mean, it's an orange like this. Well, we will see how we do that. So we call this sample or these observations instances, for instance, a training set. And this is in one types of problems, as we referred to, the supervised learning, where the ground truth is provided. So you have these objects, we call them a training set, and they are assigned each of them the name of it, because we know where it's brought up with the data. And so we want to classify these oranges, and we look at what we call the attributes. Now, think of it this way. I mean, there are two approaches. If you refer to the example that I used of a student who is coming late to the classroom, and he or she sat next to a fintech student, and straight away I would predict that they are, or this newcomer is a fintech master's student. But also the other approaches would need to consider the attributes of such object or such a human being or student coming in, which is, their background, they study the courses they choose, their marks, the bachelor's degree, and so on and so forth. These are called attributes. Now, if you have, for instance, if you go to finance and you have transactions or insurance, say driving insurance or car insurance, sorry, they look at certain attributes related to the driver and the car and the location and where it is parked and how safe that is, statistically speaking. And so think of it. If you are a teenager, you are more likely to pay more for insurance, because statistically speaking, you are at higher risk category. And if you say, for instance, if you live in a mansion which is, if you are Tory and live in a mansion and it's locked and there are security and guards and whatever, or then you pay less because it's secure and it's not going to be robbed or whatever, stolen. So yeah, these are the types of things that we call attributes. Now in the examples that we are looking at here, you can look at the color. I'm simplifying things. So the color of the object, its weight, and its texture. How do we align things and put things together? Well, actually, this is how we see things computationally. We usually have records, or say tables. And those tables usually, each record or row in the table has got a few values that correspond to the different columns. Okay, those columns are usually called attributes. So the column from now on, from today onward, we will call them attributes. So the color, which is the column name or column name, is an attribute. Now, each attribute is essentially, or hopefully, we'll be assigned a value, a distinctive value, or a unique value. Not necessarily unique that it's not redundant for other objects, but actually for that particular, you have one value. So the color would be 3. Now 3 is digitized. Let's say it can be like red or orangey or green. So if you'd want actually to do white is 1 and black is 2 and red is 3 and so on and so forth. Okay, again, this is just an example. Now weight, say here in grams, and so the weight is an attribute. The weight being 130 is a feature. There's a convention. Okay, now each row or record is called a sample in statistics, or observation. Why we call it observation? Because we know it. I mean, it's provided to us, and in this case also, it's got its type, it's orange, so it's observed, it's common knowledge. Um, and this and obviously, how do we put things together? They are represented in what we call a features vector. So each instance has got essentially is the raw aligned this way, like as a vector or a matrix of one dimension. And so this is how we usually do. So if you want to look at the transaction, for instance, or not the transaction, the example of the insurance, you would see, well, that Hisham is being insured as a driver. So it's his name, it's his age, place of residence, salary, other sorts of previous claims, with regards to insurance, i.e. my historic record in terms of traffic or accident events, and so on and so forth. Okay, cool. Now that is one observation, and then usually you have multiple objects. So if you refer to this one, you have many objects, and so you'd expect to have multiple instances. Now relate this to the tables that you might have dealt with in the past. These x sub 1 or x1 for short would be a row, a record. X sub 2 or x2 would be another record, and so on and so forth. So Hisham would be the driver and insured, and Jack would be driver number 2, x2, and Laura would be x3, and Nadia would be x4, and so on and so forth. Well, and here are the objects that we have. We have also a banana, and the banana does have different features. Of course, the same set of attributes, but different values to those attributes. And it would correspond to sample or instance or, object number 2. Okay, and usually those are drawn from the distribution of samples or objects in planet Earth, or say in the city or in franchise. Okay, if we are dealing with this problem. And so they belong to this set of the real population, let's say. Cool. And so this is how we put things together. You have record 1 for the orange, record 2 for the banana, and essentially we put them in what we call it a matrix or the table. The table is a vector of features vectors. So each one of those components, x1 to the transpose. If you don't know what transpose is, essentially it is you flip the matrix, okay, dimensions. So essentially this is the row, this column being put in the shape of a row. So if you look at x1, it goes from top to down or up to bottom. I don't know how to say that, but then you flip it on to become a row rather than a column. Okay. So essentially, what you have here, that real population or the data, the objects in say franchise, are the orange, the banana, x1 transpose, x2 transpose. Now forget about transpose. If you the last time you checked on simple maths stuff was 100 years ago. I'm just putting things together to show you what the table is, Okay, cool. And so essentially what we end up having here is all those instances, observations put in a matrix of features vectors. So here actually I was faster than the slides. Here x1 or x1 transpose is 3,132. That correspond to x1 here on the left side, which is 3,132, the column, okay? And so on and so forth. Now, this is essentially, again, these are the columns in what conventionally could be referred to as table. And each one of those horizontally, 3,132, is the row or the record in a table, okay? Now, as simple as this, you see on the right side of the panel, this is how you probably, if you did programming for data science, you are familiar with NumPy module and how you define an NumPy array, and the, say, multidimensional array, or in this case two-dimensional array, you can write down the example that I'm showing you here with simple code. Okay, so this is NumPy array of well, 2 elements, 2 observations, and as I insert that data itself, it defines the dimensions itself. Okay, of the array or the matrix. Cool. So this is how we generally find data, or if not, we actually digitize data as such. And data of what? Of the different types of problems. We will see this with a few examples in the following session. Okay, so now we can see that this is the type or the representation that we deal with. We deal with vectors stacked on top of each other in what we call table or matrix. Now, in the type of, or the one type of the learning problems that we will thoroughly deal with is called the supervised learning. The supervised learning, if you can recall, we mentioned that the ground truth or the labels, the annotations are provided side by side with the observations. So you have the attributes or the features. So their features here are for x1, or the first observation would be 3,132. They refer to the 3 different attributes that we have, which is the color and size and texture of the fruit or the object. And obviously you have another vector, which is y in this case, what we call the labels vector or the ground truth. Now, this is essentially provided with the data. It's like each record, there is, for each record, there is a value, or let's say a column value. It's called y, or the ground truth, or the label. In this case, we are concerned or want to learn whether this is an orange or otherwise. So if it's an orange, it is assigned the value of 1, and if it's not an orange, it is assigned a value of 0. And so in our case here, the first x1, x1 happens to be an orange, and therefore the first element of y's matrix or vector is 1 because it's an orange. Okay, and so here essentially I'm showing you what it is. An orange is referred to 1. Now this is an example. It might be 2 an orange, it might be 3. But the idea here is this is a simplified example of a binary classification whereby I can see now 2 matrices or 2 vectors, let's say, or a matrix and a vector. One where the observations are stacked on top of each other. I'm talking colloquially here, on top of each other or shuffled, it doesn't really matter, in this case at least. And then you have a corresponding value in another vector that we call the labels vector or the ground truth vector. Okay, now how does that relate to real world problems? How are, in the different application domains that we'll be dealing with? We'll be dealing with health-related data. We'll be dealing with fintech or finance-related data. We'll be dealing with fundamental computer science kind of types of problems, like natural language processing, like voice recognition. We may be dealing with automation problems. We might be dealing with optical character recognition, image processing, fundamental computer science kind of, or applied computer science types of problems. Okay. Well, let's see. This is the example of the optical character recognition. If you remember from the first lecture, we showed you some applications whereby, manually written digits could be digitized and read as images, and therefore we could use machine learning to classify them into numeric values that the computers can process and automate. And so if you look at the one here, one is essentially an observation, so it's essentially an orange, but it has a 2-dimensional kind of matrix or vector of attributes or features, sorry. And so the orange, if you remember, did have size and color and texture, and this one has got a value of the degree of grayscale, or how dark or bright the pixels color is in a given screen. okay? So, or image, or cut of an image. And so this is basically an observation. The one written here is an observation, is an image, and essentially it's represented with a matrix of features, and the attributes would be the pixel location. So where pixels start and where they end, usually the pixels start from one of the sides. I believe it starts from the left, the top left corner, and then you go filling the things. And so you'd see that at the grayscale, where the one is located in the image, you'll find that the values are closer, or further from zero. Zero being not colored, i.e. white. There's no painting or writing on it. Okay, and so if you want a model to train or to learn a classification, what you want is a sizable amount or a good amount of those images of digits and their representation. And then, of course, you'd want an algorithm that maps those values of the pixels, the color, the scale of the color on those pixels, i.e. the attributes, to the right label, to 1 or 2 or 3 or 4, just as how you would be mapping the texture or the color and size of a certain object to the type of fruit or object it is. Okay. You can look at the graphics also. They are represented by the matrices, and usually the matrices include the color of the pixel. Actually, it's the color on that particular location on the display, and so this is I believe Mario, if you have ever done Mario Karts in the past. And essentially what we have even in graphics, whereby you have some motion and some transitions and stuff like that, and frames and whatever, the difference between one frame and another is basically the color at each or on each pixel on the grid of the display. Okay, so you think of each object of those is an observation, if you will, and through the transitions, in this case, probably it's not something that we want to dwell on much, but essentially what I want is that the representation does not differ. It's a matrix of values assigned to the different attributes, and the attributes being the pixel location. Now let's go to a different application, whereby which is the natural language processing, and you've heard about natural language text mining, for instance, or information retrieval. In the past it was, and there are many ways of representation. Now, of course, you also heard of advances very, very recently in natural language processing, where people are saying that it is becoming scary nowadays, which to an extent I think can be. So one simplified approach to representation is called or could be referred to as term occurrence. So how many times a certain word has appeared in a certain text. And so rather than dealing with words themselves, like bats can see via echo, whatever the word is, I don't know what is this? Echolocation or echolocation, sorry. See the bat sight, sneeze. Okay, whatever that means. The thing here is that how do you deal with this? Well, this snippet, say if you think of it as a tweet, and for applications of sentiment analysis, you look at the tweets like short text provided. What you do is you have a vector, and each vector location has got a number, and this number refers actually to how many times a certain word in the English dictionary has appeared in this text. Okay, and so you could imagine of this vector at the bottom, this array, let's say, could be the length, or say the magnitude, say the length, to simplify things, could be the number of words in the English dictionary. Okay, so you would say how many times the appeared, how many times we appeared, how many times can appeared, how many times. And obviously, every text will have a different vector accordingly, because you'll have different components or structure of the text that makes it unique from other text. And both vectors will be similar or equivalent or the same, essentially, if the text is the same. Okay, so that is a representation of the text. And obviously, just as we dealt with the orange, you can deal with the vector of that text and find similarities, find patterns, find so on and so forth that we'll be learning along the way. Okay, so that is one approach. Of course, there are other methods, because due to efficiency, and I referred to, for instance, the noise that problems dealt with by dimensionality reduction methods. Sometimes some of the words actually mean, I mean, if you are the information retrieval, you actually classify texts of books, for instance, or journals, or newspapers, and how do you classify untagged kind of news pieces or blogs into subject areas? You'll have to go through lengthy text, and so probably computationally and in terms of the efficiency and the effectiveness of learning models, you need to find better ways of representation. Nonetheless, it doesn't differ in terms of the mechanics. You have a vector whereby you have an element or value that represent in each vector that represents each word. Okay, like more advanced concepts of representation of the text, again, it goes into vectors, but I mean, it translates into vectors, but it can be also some sort of a squeezed or reduced, compressed kind of representation that not only considers the syntactic or syntactical component of language, but also the semantical or the semantic component of the language. So, for instance, you would want to say, I don't want a vector of the length of the English words in the English dictionary, but rather I want a squeeze, like a smaller, say, 100 words. And those 100 words, those words are not really a word in the vocabulary, it's a notion, a concept. So you would say a verb, a location, it can be a discipline or job. And so all the words that relate to job or location or whatever would be clustered together, would be put together in that particular place in the vector. Okay, so that is a smaller representation and much more semantic aware kind of representation. But nonetheless, what I want to get to here is at the end of the day, it's a vector of values, just as the color, size, and texture of the orange is. Or a transaction, like a bank transaction. It's got a time, it's got amount, it's got a recipient, it's got a sender, it's got a medium for transaction, it's got receipt. So all those could be values, numeric values, and that they correspond to the role of that particular observation, of that particular transaction. Okay, well, look at another application whereby we look at we do voice recognition, for instance. And I mentioned in the first lecture that it is one of those problems that we learn, humans, but we can't explain unless we are experts or practitioners or scientists in the field, or voice engineers or whatever. Excuse me. So so at the end of the day, the voice actually translates into a vector whereby each value represents the the amplitude of the sound wave at whatever frequency, and so this is how the machine would be able actually to deal with, or the algorithms, the learning algorithms would be deal with the different observations, i.e. the different voice pitches or snippets. Okay. Apologies if my English is not really correct here, but this is how far I can go with English. Cool. Now, back at it. Let's take that the simple example that we put forward, because we wanted to build a model that classify orange from the rest of objects, and we refer to this as a supervised learning problem, and it's a classification problem. Now, we also have other types of problems whereby the output is not essentially 0 or 1 or a binary, like yes, no. It can be numeric. So, for instance, the classification of the orange or not orange, or say high risk, low risk in an insurance categorization of customers. This is high risk, this is low risk. For instance, if you have this as and the classification does not necessarily need to be binary. It can be high risk, low risk, medium risk. It can be multi-class kind of type of problem. Nonetheless, it's a discrete categorization of the observations into different class distributions. On the other side, you have different types of problems like the regression, and so the Y is continuous. The Y is the outcome, the thing that I'm interested in learning. So I want to actually map certain set of features into a certain value, and this value could be conventionally be referred to it as Y. And so if you want to take the example here, simplified even further, a classification problem on the left would be, will you pass the exam? It's yes, no, or maybe I don't know. And the regression problem would deal with a learning task whereby how many points will you get in the exam? And so this is a numeric value. It's a continuous value. It could be 30 and it could be 30.5, okay, of 100. And when I say within a valid interval, you can't get in the marking a -3 because it doesn't make sense. So also you sometimes need to learn the validity of the interval, and I'm simplifying the terminology here. Okay, cool. Now look at how we find the data. We find it in different shapes, really. Sometimes we shuffle it, we restructure it for our algorithms to deal with it very easily. But at the end of the day, you have two matrices. One is where the data features are, and usually there are rows, records, basically. Every value corresponds to a certain attribute, and the attribute would be what we refer to conventionally as a column if you talk about Excel sheets or whatever, or database shenanigans. Sorry. And then the Y would be, essentially, this is in a regression problem, so you see that the Y is a value. So if you take the first row here corresponding to the temperature in the previous day, so each box is a day in the past. So 1 is yesterday, 5.6 is the day before, 3.4 is the day before, and so on and so forth. And then 1.6 is the temperature of tomorrow. Okay, or say 1.6 would be the temperature of today, and 1 in the X matrix would be of yesterday, and 5.6 the day before. And then the task here, okay, I have this. Would you be able to predict what will happen tomorrow in terms of temperature? Okay, now let's formalize things and go and do things structurally. The process, you'll be hearing about training, learning, algorithm, or building a model, and testing and validation. Okay, well, training is the process of building a model, learning a model. And this model could be a parametric model. So you need to learn certain parameters that map the set of features to the grounded truth, okay, in the supervised learning world. There are certain motivational kind of concepts that I will explain once I see you, hopefully next week, in class. But for simplicity, let's take it a high level. When I have those objects on the right side, I want to learn from their attributes, from their characteristics, what they are. Okay? I call them a training set. Let's assume that all of them will be used to train a model. And then when I say learn an algorithm, is essentially taking the features, each object's size, texture, and color, or size, color, texture, come up with a hypothesis, as you see it in red here. This hypothesis, we parse those features to a hypothesis, and we say, okay, well, I'm coming with a hypothesis like this. If the texture is of such and such type. I'm short of terminology in English in order to use the example of texture. What types of texture there could be? Many types, I don't know. But let's say size. So my hypothesis for learning, I'm coming up with an algorithm here. My hypothesis would be if the size is less than 300 or 10 grams plus 3, and color is not bluish, not whitish, not black, it is an orange. Now that is a hypothesis. It is a hypothesis based on what? On the features of the object. So numerically, I look at the values in the vector, and I will say, well, my hypothesis is this. Now, it's a guess. A hypothesis is essentially as the interview that I showed you as an example, the joke, the first lecture. Now, those values that you relate to the features are called parameters, model parameters that you need to learn. And the model parameters that actually predict the right ground truth would build the model. That simple, okay? So if the outcome or the output is a class, then you want that output to be a category. And so here is a hypothesized model or a learning algorithm. So the hypothesis here, just as I said, I take the two features or the two attributes, weight and color, and then I say, well, this is a parameter that I am putting here forward. If theta sub 0 or theta 0 plus theta 1 times the weight of that observation greater than a certain value, and the color or of that observation equals a certain value, then it's 1, i.e. orange. Otherwise, it's 0. Okay, well, this is a hypothesis and this is a model. So I create this model. And this model is this curve, as you see on the top right, on the right, bottom right side of the slide. And so essentially I worked out a learning algorithm on the basis of two attributes. One of them is the weight and one of them is the color of the orange and the other objects. I plotted all the observations. I know the ground truth. The ground truth is reflected in terms of the color and the shape of the observation. So this is essentially a non-orange, the X, the cross, and the blue circle is an orange. Okay, and so this is, you see that I plotted them on this Cartesian or two-dimensional plane, and they happen to be like that. What I'm learning here, my hypothesis, is this curve, dotted curve. Okay, and then if I have other objects, I can test my model and I can give an indication of how accurate my model is. So if I have other observations that I did not use in training my model, I basically can say, okay, well, here are some hidden observations. According to your model, which I see here, if theta 0 times whatever, then it's 1, otherwise it's 0. Test this one, and I call this a testing process of my hypothesis. But essentially, this is the whole idea. You guess. Of course, there are assumptions and there are models that they are, built, and we can use them, that they build discriminators or decision boundaries, just as this curve that separates the blue circles from the red crosses that we'll be using and learning in this module. Okay, this is a classification problem because I'm concerned about classifying whether this is an orange or otherwise. Now look at another hypothesis, but for a different type of problem, which is the regression. Now the regression is something like this one, which is how many points will you get in the exam. So y is continuous. You have a value. So if you go back here, it's a value, and the value is could be represented by a curved line. This is the function, okay? And so you can take the orange in this case, say there is another attribute which is called the price of the observations. I think this is an example from Andrew Ng from Coursera, the plot. I mean, and so the example he uses is the house prices, but you can relate it to house price or the orange or the price of the orange. I don't know. Oh, sorry. Yeah. He's trying to predict the house price from one feature, or one attribute, which is the house size. And so, in our case, we would want actually to predict the price of the orange as a function of the orange's size or the object's size. Okay. Well, this becomes a regression problem because the outcome is numeric and it's continued. Could be anywhere on this on this blue line or curve. And essentially, you can come up with a hypothesis of a linear function similar to this one. This is a linear function. So this is a linear regression model. I'm saying that the outcome, which is y, hypothesis, passed to it is the set of attributes or features of sample 1 or instance 1. And I learn certain parameters, which are theta 0 and theta 1, which is essentially the intercept and the slope or the gradient. Okay, cool. So we will talk about linear regression models in the future anyway. So here we learned, or we came up with two hypotheses, essentially one for a supervised classification problem and another for a regression. If you want to see what the hypothesis is, like for the regression one, the slide that we are looking at, the blue line on the bottom right side of the panel is basically the linear regression model or the model, what I learned, okay? And the observations, so the different oranges and their prices are plotted by the crosses. So I learned this model, which is this blue curve, on the basis of the observations that I have and the ground truth, their prices essentially. Now let's go to some definitions and conventions. These are to help us when we go deeper into the different algorithms and learning tasks to relate to what these conventions relate to. So you have the thetas. Sometimes you find them as W's and the small W's as like weights for the weight corresponds to each feature. So if you look at here, for instance, the theta 1 corresponds to the first, let's say, feature of instance 1, okay, which is, say, the color or the size. So it could be weight or theta, it doesn't really matter, or beta, be it doesn't really matter. But these are the model parameters that I usually learn, or we need to learn in order to generalize, in order to map the set of features to the desired outcome or to the known ground truth that corresponds to that particular or to each particular instant observation. Now, if you want to look at x0, x1, x2, xm, minus 1, whatever, this is the training set of size, say, m. And so each x is instance. You can go further level down to say, well, x1 is essentially an observation, but x0 is an observation, x0.0 is observation 0 or what, or the first observation, attribute 1. And attribute 2 would be 0.2 or 0.1, and attribute 3 would be for observation 1 would be x0.2, and so on and so forth. Okay, it doesn't really matter, but as long as we can refer to an instance is an x, let's say. That is drawn from a distribution, which is the real population from where those observations belong or came from. Now, in this case, each instance is essentially represented as a vector, and the vector has got two things, the magnitude and length. And this is why if you want to correctly annotate or use a correct notation for a vector is with an arrow that describes the direction. It's a vector, okay? So it's in say in a two-dimensional space, you see an arrow going from one place to another. And this, which represents basically the features of the corresponding instance. Okay, we will see that again if you are not familiar with how vectors are represented geometrically. H, sometimes you find it like f function, or sometimes you find it like g. It doesn't really matter. It's like the hypothesis. It's the guess that maps actually the vectors of features to the vector of ground truth, which is y in the case of the example that we used in this lecture. And the process of finding a hypothesis that maps that features to the ground truth is called basically fitting a model. So fitting or learning a model is the process of adjusting, or let's say learning, the certain parameters, model parameters with the different assumptions like theta's 0, 1, 2, whatever, and relative to each feature, and with some calculations, you'd be expecting the result to be the ground truth that I can actually test because I have it provided with the data. So if you would want to look at the structure, you have the observations aligned on the top, on the bottom of the slide. You have the observations represented as vectors of features, and then the model is the hypothesis in the middle. The hypothesis takes that set of features for each instance and then learns certain parameters like thetas that relate to each feature of that particular observation. And you need to learn, if it is an orange, you need to learn 1. If it's not an orange, you need to learn a 0. Okay, so you keep guessing until you find those thetas that essentially map the different objects to the correct label that is provided usually with the data. Okay, so the process, if you'd want to put it with formal notation, is that we have a training set, which is a pair of observations and their labels, the ground truth. So the xi is an object and yi is the corresponding label. So if it's an orange, xi would be orange 1 and yi would be orange, the word orange, or 1 in our case. And this is drawn from that is the assumption. It's drawn from a distribution of objects. So if we are dealing with, our problem is to look at the objects in franchise, so all the objects, all the, the small objects in franchise or on campus, let's say, and all those objects, what I'm dealing with on the left side, I'm dealing with let's say a sample, because you usually don't have access, or most of the time you don't have access to all samples or all the population. You have a sample to learn and generalize from. So it's drawn from a distribution, and one of the assumptions that we usually rely on when learning models is that independence and identical distribution of the samples. So we usually assume that that I'm dealing with those particular samples in my training set, that the probability that one of them is with me has nothing to do with the probability of the other sample being with me or otherwise. Okay, so that actually is a fundamental assumption for mathematical convenience, let's say, because many of the models rely on, for the calculation, for instance, the probabilities, the product of the probabilities rely on the assumption that the events are independent from one another. Okay, so the idea here is that I have a sample. In order to generalize on the real population, on the real problem, if you remember, I trained my model on 10,000 MRI scans of chest, let's say, or breasts, for instance. And then what I want is the learned model to be used in real world applications. So for the coming million MRI scans, I want a prediction whether it's a benign or malignant. Okay, and so the 10,000 that I use to learn my model, each sample or the samples should be independent and identically distributed. i.e. not arbitrarily broad, but like they are not really, there's no correlation or dependence between one observation and another in my sample. And so essentially what I refer to, that xi here, is it's drawn from, or it belongs to a multi-dimensional, let's say, set of values. And so the n would be the dimensions of the features. How many attributes? How many attributes? So xi, for instance, the orange would be texture, color, and size. And so n would be 3. And so you have a vector of 3 values, let's say, for each observation. And y would refer, in the case of regression, for instance, to the r, and in case of a binary classification, to either 0 or 1, say. And so what the process of learning, the learning part of machine learning, is that we want the algorithm to learn a mapping that approximates the features of a certain instance, like here xi, to a correct, the correct label. Okay, and well, can I learn? Yeah, of course, because I've got hold of xi yi pairs, the sample that I am using to training. That is the process of training a model. Essentially, I'm saying, okay, take these parameters, the thetas, and let's assume that this is, a regression. So it's an assumption. There is a linear association between the feature and the outcome, the feature value and the outcome value. Okay, cool. Well, go and test with theta 0, theta 1 being this value, and see if you can predict the existing yi. I mean the label that is provided with that particular observation. And okay, if it's not, change the values of theta 0 and theta 1. Try another value, another pair of values for theta 0 and theta 1, and so on and so forth, until you get to the point where you can actually reduce the margin between the predicted by your mapping model, the f function, and the ground truth. Okay, so this is structurally how we go about the supervised learning process. Okay, if we can have multiple thetas, i.e. multiple models, which are hypotheses, as we agreed, so you can come up with how many hypotheses? Like really a very huge number of hypotheses you can come up with, even more than what you can imagine. Okay, and so each of those hypotheses produces a model. It's a guess. Okay, and the question usually, right? So which one is the model that I will use to generalize? Okay, there are a few things to consider. So we need obviously to evaluate the models that we produce, or the guesses, the hypotheses that we come up with. Obviously, in a supervised learning context, you have the ground truth. So how much each guess diverges from the ground truth is an indication of how good or bad the model is performing. Okay, and so here you have model A and model B, and you have one hypothesis, which is what I described here. I mean, those values for thetas do provide in A this curve, and relative to the weight and the color, for instance, and in B relative to x1, it gives you this line. But obviously, you can have multiple models. So you have for A, you have 1 and 2 and 3, and seemingly the 3 of them do quite a good job at classifying the objects, orange from non-orange, so, or high risk from low risk if you are doing insurance classification. Okay. So on the right there is more blue objects, say the oranges, and on the left there is the non-orange. And the question is, okay, so which guess should be my model that I'll be used? And these are the things that we will learn. But I think most of you would pick, for instance, number 1, because it seems, even though it doesn't really classify all of them, but it seems much more smooth, perhaps close to perfectly accurate, but it's not very complicated as the one of the one in 2, which is the zigzaggy one. Okay, well, why? We will learn why, but essentially a simplified model is usually more generalizable than a complicated model, okay, due to problems we refer to usually as variance problems. That needs really very thorough explanation. I will mathematically show you in the coming session, hopefully. But that the problem of variance is comes from the assumption that the sample that you use in order to train or learn or come up with a guess hypothesis is only a sample. And this sample can actually have noise or can have some representation problems, to refer to it in simple terms. Which means if you adjust your model to be really very tight, very attached to the very, very granular, let's say, differences in the features, then you are making your model tied to that sample in particular. And it turns out when you want to generalize to the real population, this model wouldn't be as accurate as it is on this sample. So you'd want to think of a less complex model, i.e. loose or more loose, let's say, than a very fine-grained, tight one to the sample, on the basis of the assumption that you're only learning on a sample that is not entirely representative of the real population, okay? And it turns out that generally, a less complex model is much more effective and accurate in real-world application, okay? And we can actually quantify this and see it when we train our models. So there are ways to avoid this problem of variance, of having really a very complicated model that works on training but doesn't generalize well. Now, model B, the same applies. You'd go, for instance, for number 1, or probably maybe not 2. Again, these are just examples. I mean, 1 or 2, either of these would be my model. Probably 2, because 1 seems to be very, very simplistic. Okay, and that corresponds in the problem A to number 3. It is simplistic, so you'd want to be not very complicated, but you don't want to be very loose, i.e. very simple. So number 3 in the example A is simply a straight line. A straight line is a very simple model. It's a linear model, essentially. Linear model, I mean, it's defined by 2 parameters you need for a simple linear model, okay? Well, it's the intercept and the gradient, or the slope, sorry. And so simplistic is what we call, produces a problem or of what we call the bias, or high bias. The word bias comes from you are biased towards an assumption. You come up with assumption that there is a linear discriminator that separates 2 class distributions in the case of A, for instance. So you are biased towards, you are enforcing that assumption, and therefore you are after a linear model and you use it as a discriminator to separate both class, the different class distributions, in this case binary classes. And so all will turn to depend on whether this assumption is valid, whether it really mirrors the class distribution in the real population from where this sample that I used to learn my model is drawn from. And it turns out if you go with solid assumptions, like with strong biased views, your model tend not to generalize well equally. So if it is too complicated, you are being tied to the sample and its characteristics, and you tend not to generalize well. And if you are too loose, you also tend to be, enforcing an assumption about the distribution of the classes, and you tend not to generalize well either. And therefore, there should be somewhere in between, and this is why we picked, say, model number 1 in the A problem, because it's in between. It's not that complicated and not that simplistic. And the same applies for B. So I pick number 2 because 1 is entirely simplistic. There is that some curvature in the crosses, the shape of how the crosses are plotted, excuse me. But at the same time, it is it can be represented by a less, let's say this is a quadratic, let's say, curve in number 3. So a less zigzaggy, if I may say so, curve like in 3. So number 2 would be my pick. Okay, so essentially, as I'm training or coming up with my hypothesis on the training set, I need to be looking at how my model would generalize on the real population, the distribution from which the sample I used to train my models have been drawn or has been drawn. Okay, and so in formal terms, I want a mapping function not only is good at the training set, but also for observations that come from the real population that I did not use to train my model, also to give the right answer. I.e., I trained my model on the MRI scans for the 10,000 MRI scans. It gives me 95% of accuracy. Let's say every time I pick an MRI scan, it would map this set of pixels or image to whether it's benign and malignant. And now when I take it to deploy it in the real world, I want it to give somewhat close to the 90% accuracy in the real on the real observations, on the real world observations. Okay, how to do this? We will learn how to approximate the general model accuracy. We can't really assess it perfectly because we don't have access to all observations that will come in the futures, but we can approximate it, and I will explain this to you in the weeks to come. So in order to pick the model, we will need to evaluate what we call the goodness of fit. And for now, we can call it accuracy, because term accuracy is actually a relative term, and that's why I put it in between quotation. But anyway, so how good the model is. What model? It's the hypothesis, the guess, the function that maps the set of features to the desired outcome or the ground truth. Okay? And as with the previous images or plots about particularly these, which model or which hypothesis should be the one. If you look in general terms to translate what I said, if it's too complex, it won't generalize well, and if it's too simple, it won't generalize either. The two types of problems, the high variance and high bias, are referred to as overfitting and underfitting. Okay? And so if you take that curve, that blue curve, as the accuracy of the model, i.e. how much the learned or the hypothesis maps the features to the ground truth, or how much divergence there is between the ground truth and what my model is predicting. So I look at the texture, size, and color, and let's say this is orange. Okay, yes, if it's orange, then the divergence is 0. If it's not an orange, then the divergence is 1, because I have the values 1 and 0. Say that is in short. So during training, the more you complicate the model, that better the accuracy is, because you are learning, you are growing very granular. Okay, it's like I usually use the concept of Play-Doh. So the Play-Doh and say I want to put an object on a Play-Doh. Play-Doh? Am I pronouncing it? Oh, okay, Play-Doh. And so I stretch an object on I fit an object on a Play-Doh, and I say, well, this is the stamp or the finger. How to say the footprint? It's the print of a certain object. So an orange will create, say, a circular kind of print. A banana would be an oval, let's say, or yeah, and I don't know, another triangle will create a triangular shape. Okay. Now, if they happen, if you keep learning the print for each object on the training, you would end up having all the corresponding fits or prints to all the observations. And so every time you have an object, you put it there, the Play-Doh, and you say, okay, it corresponds to a triangle. Okay, maybe not the size, this size of the triangle, maybe the other one. And so you end up having an accuracy of 100%. When you generalize, i.e. when you test it on real-world observations that were not used to create these prints, you will find, okay, you come up with a Caribbean orange, which is of the size of a melon. And it doesn't really find a place in the fits that you created on your Play-Doh. And then the model. Now that is why is it caused? Well, the characteristics of your sample, they are not representative of the whole population, okay? And so you don't want to be very complex in this print. You may need to make it a bit loose. Okay. Equally, if you make it very, very loose, and you will see example now from TikTok, you end up having an underfitting or high bias problem. And so the print will be so loose, so the model or the print will not distinguish between an orange and, say, I don't know, a lemon, you know, because it barely leaves a print on the Play-Doh. Okay, and so usually what you want is to find a model somewhere between, because essentially somewhere between what you'd call, for instance, the sweet spot is the best model in terms of generalizability. Okay, so I think I referred to this, but I'll show you this example from TikTok about underfitting, which is the high bias when the model is very, very simple. Let's see if it shows.
This is a square.
This is a square.
The square.
The square.
That's right. It goes in the square.
Yes. Yes. Okay.
And how about this rectangle?
And how about this
That
rectangle?
one
Also the square. Also the square.
goes
Yeah.
in there too.
Yeah.
Up next,
We've
got this thin rectangle.
the thin rectangle.
You guess
The
where
thin
that goes?
rectangle.
That's
The
right.
thin rectangle.
That's right.
It goes in the square hole.
And up next,
A
a cylinder.
cylinder.
I think that goes in
The circle.
the
square hole.
Now, we've also got this semicircle right here. Do you see a slot that would fit
The semicircle. The semicircle. The semicircle.
That's
The
right.
semicircle.
The square hole.
The square hole.
Okay.
Okay.
Up next,
The
triangle.
The triangle.
We know what hole that goes
know
in,
what hole
right?
that goes in, right?
That's right.
Triangle.
The square hole.
The square hole.
And up next, we have the arc.
The arc.
You guessed it.
You guessed it.
It goes in the square
It
hole.
goes in the square hole.
Well, that is essentially what I was referring to with the Play-Doh. You see, that model is so loose, so any other object would fit into the same, let's say, class, and therefore you don't want it to be very, very complicated. In this case, complex would be very, very tied to the size of those objects. So regardless of the shape, the size, and very loose would be so wide so that any object can fit in any of those shapes. Okay, that is in a tangible analogy, let's say, the problem of underfitting and overfitting. Now, overfitting, if you want it scientifically speaking, we would say, well, it's an indicator of how much variance there would be if any model is learned given a change in the data set. So we refer usually to this consistency or stability of the model. So the model is stable, is the model of low variance, which means that regardless of the difference in the sample distribution, the sample itself, the learned parameters, the thetas that we will learn will be essentially the same or roughly the same, okay? So there won't be differences between them. It's like the model would be the same regardless of the data which is trained on. Okay. I think I explained this. All right, so the Andrew King agrees with me. The optimum model, or I agree with him. The optimum model would be the one in the middle here, which is not too complex and not too loose either. Cool. Regularization. I think I will skip certain things about regularization. However, for the most part, you'd find that the models in estimating or learning the combination of parameters. So if it's a parametric model, as a linear regression model, you need to learn theta 1 or W1, which is essentially the slope, and W0 or theta 0, which would be the intercept. Okay. Basically, you can have different pairs, if we are talking about two parameters to learn, different pairs that can produce the same solution. Okay, so it's like many solutions to the same problem, and which solution, which translates to which model then we should pick. And this is an optimization actually process, which is called regularization, whereby we can determine, say, the best values for those parameters, essentially correspond to, it's a compromise, like an optimization between the accuracy of the model and the complexity of the model. And we will learn certain types of the regularization here. You can see the L1 and L2. Cool. And now let's go to the evaluation. How do we do it structurally? You have a sample, so in the left side, this is the data that you have, and we usually split the data into two subsets. And in each subset, you have, in a supervised learning context, you have the observations, the instances, and the corresponding labels or ground truth. So each row, each object, and its type, an orange, non-orange. That would be the training sample and the training label corresponding to it. You learn a model, and then you keep iterating. You come up with different hypotheses, or hypotheses. So how correct, how divergent, how do your model outputs diverge from the ground truth or the labels? And then you keep guessing, and then you reach a certain point where you say, well, okay, I'm quite correct here, 95% of the time, I'm correct. And then there is the other split, which is other observations that you did not use to learn the model. So it's not in the first part of this, the top side of the slide. You call it test samples or test data subset, which is other observations and the corresponding labels to those observations. Okay, and so you do what the model or the best hypothesis that did well or did on the training, you use it to predict those new samples, and you check whether they give you the correct labels or ground truth or not. And then accordingly, when you do a sample of those, like a set of those, you have an indication of generalizability, error, or accuracy. So you would say, well, depending of course on the size of the data set, I told you earlier I will put this in mathematical or formalize this later on, but later on, like next week and the following ones. But for now, this is the structure. You split the data that you have with the labels, you train on one part of the data, and then you test on the other part of the data, and then your testing results are an indication, or it's called an approximation of how well your model will be doing in the real world. I think I already explained this. So there's another component or concept that we use or practice in learning models, which is called the validation. And we will learn about the cross-validation because, as I mentioned, there are parameters to each model, even the same type of model. So even of the regression model or logistic regression or support vector machine for classification, there are different parameters, and then you would want actually to test multiple times before going to test on an unseen set of data to give an indication of generalizability, error, or how well and on the real population the model will do. And this process is called validation, and it happens during the training or the guessing or coming up with the hypothesis. And usually we use these to hyper-tune the model. So it's like to tweak the estimated parameters, to tweak the values of those theta 0, theta 1, theta m minus 1, for instance. Okay? This is why we call it, like in number 2, it's called the hyperparameter optimization using the, something which is called cross-validation. There will be a mini session on cross-validation that will follow. Okay, I'm skipping this. Again, these are the typical things that you'd find on Google of how structurally to explain the splitting and the cross-validation and where things, where we are. We basically are at the building model and the models. And so we haven't yet done validation, we haven't done hands-on or went to splitting test and train data set. We didn't do hyperparameter tuning. We're just looking at the bigger picture of, coming up with a hypothesis, which is the model here, the blue box, okay? So don't worry if all those things seem very, blurry and confusing to you at the minute. Okay, now the different performance measures in order to say if we are here, how correct each model is on the training set and then on the test subset of the sample, we need what we call performance measures. And for the different types of, learning, we have different types of performance measures or indicators. So for regression, you can think of the mean square average error, for instance, okay, or the mean absolute error, which is essentially, if you think of the square root error or mean square root error, which is for regression you are predicting a value, numeric value, and so what you would want to use as a performance metric is essentially how far your prediction is from that real recorded value on the historic data, of course, and you sum for each point you sum the square divergence, the square difference, okay? And why? Well, there are many reasons. We will come to it later on, but essentially, when you square them, the negatives, the ones that come below the curve, do not cancel the ones or the divergence that comes on top of the curve. That's one example. And another example would be that you are concerned about the high divergence, because the square would magnify actually this divergence from the very, very tiny divergence from your model. Anyway, so that is these are examples of the performance measures that we will be learning. We are not learning all those, but we will learning many of them. In classification, we will use the confusion matrix. I'm sure that you heard at least of what the confusion matrix is, which is confusing, but also derivatives of this metric or performance measure, which are the precision and recall, and the ROC AUC curve, and the concept of accuracy, which is essentially actually the confusion matrix ratio, let's say, and the log loss. Not all of them are going to be covered in this module, but many of them will. In unsupervised learning, we will look at the RAND index, for instance, and other ways of evaluating an overall model with the cross-validation error and heuristic methods for, say, to find k in the k-nearest neighbor, and so on and so forth. Cool. So here are really, again, brief examples, brief, because we are revisiting this in much more detail. But on the left side of the panel, you have a regression problem, and the real observations are plotted in dark or black circles, black dots. And so essentially the learned model, the hypothesis, is the red line. And what I test here, what I use as a performance measure, which essentially is how far my learned model, my hypothesis, which is the line, is from the real observations, which are the dots. And so what I do is every line that I come up with, because you can think of many lines with different slopes, okay? Slope going sharper on the top, or less slope, which is much more attached to the weight axis, or inclined towards it. So, and you take the sum of square differences. So you sum all those red boxes, which are, the sum of square difference between the line and those real observations. And this is called the mean square error, okay? So that is one metric to evaluate our regression model. Now, for classification problem, and here it's let's say a binary classification, the output of your classification model could be one of 4. And those 4 could be a true positive, so it's an orange and you predicted it as an orange, and that classifies that is here. And then it's a false negative, which says it's an orange, but it's being predicted as non-orange, so it's a false negative. Or it is a non-orange and it's being predicted as an orange, which is the false positive. Or it is basically a non-orange and it's being predicted as a non-orange, and that is a true negative. So 1 of 4 would be the outcome of the model, okay? And so that's what we also are learning in the weeks to come, and we are applying the confusion matrix, learning the derivatives of which, and what it means. Okay. Recap. So what we emphasized in detail today is the categories of learning, the criteria based on which we classify the types of learning. We looked up whether there is human intervention, so supervision. So you have the supervised, unsupervised, semi-supervised, and reinforcement. We looked at the types of output, whether it's numeric or classification. We looked at the density estimation and dimensionality reduction types of problems as well. We looked at the mechanisms and the frequency. And so the mechanisms would be whether we come up with a model or instance-based. Instance-based, always think of the example of a student coming and sitting next to a fintech student, and then you would predict that you don't need a model. And then we used the other example whereby you build a model, which is essentially on a plane, a two-dimensional plane would be a curve, a line, and that would be your model. And then the frequency, think of the batch learning and the online learning. And the online learning, even though that the term is not scientific, but at least we can relate it to examples. So it is one-time learning, and the model is deployed in the real-world application. And that online one is one where the learning process is continuous, and the quality of outcome depends on the quality and the frequency of learning. Then we talked about problem representation. I showed you, how an orange can be used, represented in a vector of attributes, and each attribute is assigned a value, and that makes a feature. So the texture and its value is a feature, the color and its value is a feature, and that can be extrapolated to the different types of problems. So you have vectors for voice, you have vectors for an image, and those vectors can be two-dimensional or multi-dimensional. Let's say in the case of image, for instance, it is a 2D matrix where each sample is represented, which is essentially the color of each pixel. If it's a grayscale, it can be between 0 and 1, how dark each pixel is, okay? And but it can be RGB, it can be multiple, like horrendous number of colors. And also the natural language, we saw that let's say the occurrence-based representation, whereby you have how many times each particular word appeared in the particular text that I want to analyze, and that is a numeric representation of the frequency of the occurrence times. but also you have embedding techniques whereby you relate the vocabulary to certain concepts rather than the syntactical aspect of the of language. And so on. And then we went to introduce very briefly, actually, the evaluation and the structure of learning. We also referred to or covered, or let's say, emphasized a bit the process of learning, at least in the supervised learning context, with some conventions and formal definitions. Now with the reading, that is not I'm not forcing you, asking you to read all of those. Any of those is good, and it is not really a mandatory to read all of them. We cover. I mean, if you rely on the material that I cover, that is absolutely okay. But if you'd want actually to find more or learn more, then I recommend those sections in the 3 books. And again, these are the editions that I provided in the first lecture. So the page, it corresponds to the editions that I showed earlier, because otherwise they would not, the more recent editions, the page numbers would not be correct. Jason Brownlee's blog is usually one of the best for those who want to learn machine learning from scratch. I usually would recommend people to look at his. And a good summary about a tour of machine learning algorithms is provided here, the link to it, and gentle introduction to bias and variance trade-off in machine learning, which is the overfitting and underfitting, excuse me, is provided here. Cool. Next, we'll be doing more evaluation regularization, and next week will be on similarity. Now, go and play a little. So if you start doing these exercises when we reach week 4, you'd be at least familiar with the simple tasks. This is essentially some plotting. I'm sure you did more than this in programming for data science. And here, for instance, if you'd want to start mingling or playing with data sets which are provided actually in pandas. I think it's not data. No, there's no pandas. The petal set, was the iris data set, is a famous one, used actually as a toy example for learning. It's provided in scikit-learn, so you can load it with load iris, as you see here. However, you can also create a pandas framework and table like this. Just simple things. The recommendation here is to play. Well, thank you very much, and I'll see you next week.